Hi everyone, and welcome to my talk, All the Pipeline's Journey Through the GPU. I'm Lou, I'm a developer technology engineer at AMD, and I work together with a lot of different game developers to make sure their games run well on our hardware. This talk will be an introductory talk for graphics programming. So I will introduce you to the concepts of graphics programming, how the data is processed, how it's presented to the GPU. And when talking about graphics programming and programming on the GPU itself, we also have to look what has to be done on the CPU first. So I will start with the CPU part. That's basically the top row. It's how the data gets generated, in which form it has to be presented, and how to transmit this data to the GPU. And then also how to tell the GPU what it needs to do with this data. And then from the GPU, this will be the second part of the talk, how the GPU is processing the data, what it does, and then ultimately how the output will look like, and that we get the final result on the screen. So when talking about graphics programming, the typical problem case we are trying to solve here is that you have a 3D world, and then you have a camera, you look from a certain angle to this world, and you will basically want to generate a 2D image that will be displayed on your monitor. But let's start what on the CPU side, that when you create the 3D world. So creating the 3D world, or these objects that are placed in this 3D world, you usually can use different kinds of software. An example would be Blender. It's an open source software, but there are a lot of different ones out there as well. The objects can be represented in different ways. The most common one is still that the object gets represented with a bunch of triangles. Another option would be with voxels or also generative data, but we just stick for this presentation to the most common one, which is the triangles case. And the triangle is defined by 3 vertices. And then each vertex can have a bunch of attributes. It needs to have the position information so that it's known where the vertex is. And then other common attributes would be normal vectors, texture coordinates. But there's no limit in what kind of attributes you can add to the vertex. It's basically really up to you. One thing to consider is that if you add more and more attributes, of course, this also increases the memory footprint of the vertex. So keep it as low as possible, but obviously add all the attributes you need. And then if you have your model, you can export it using some kind of format. So there are a lot of different kind of formats out there, but you can also use the custom one. Important is that you have obviously all your vertices with all the attributes of these vertices, and that you also store additionally the connectivity information between these vertices so that you know which 3 vertices span a triangle. And then if you have your exported object, you will import it to your game engine of choice. And then if you add your game engine, there's usually a game engine specific format and representation of your object. And now it's we kind of enter the realm how the CPU communicates with the GPU. So there are 2 different sections we need to consider here. First is just the pure data we need to transfer from the CPU to the GPU. And this data is the data that represents the object we just created. So we need the vertex buffers containing all the information of the vertices and the attributes. And then typically you also have an index buffer. This is already an optimization step, because if you have a vertex, usually a vertex is shared by several triangles. And one way is that you just copy and duplicate this vertex several times with all its attributes. But what you can also do is just to have an index associated with each unique vertex and then just duplicate the index. And then you reduce the needed memory for the vertex and the index buffer in total. Then you can also have some textures associated with your objects and maybe some other kind of data you need to process. You can also do some other pre-processing stuff already on the CPU, for example, visibility testing, so that you don't transfer data to the GPU, which is at the end not needed because it's not in your view space. So if the camera is pointing to a section of your world and then the other section which is completely not visible from the camera angle, you don't need to send this data to the GPU. this would be just wasted time. And these kind of data reside somewhere in your system memory on the host, and then at some point we need to transfer them to the GPU. So this is the one set of data we have on the CPU. The other one is the instructions for the GPU. So basically on the CPU, we record all the commands to tell the GPU what it needs to do and how it needs to process the data. And these commands usually also get recorded on the CPU, and then at some point, we transmit all these instructions to the GPU. And in a game engine, usually you have some sort of abstraction layer, which is an internal representation of all the different commands. And then this abstraction layer can map to different graphics APIs. So examples of graphics APIs would be the Vulkan API, DirectX 12 or 11, because it's very common that the game engine supports several graphics APIs. This is due that it needs to support different platforms, and depending on the platform, you may be even forced to use different graphics APIs. So it's always good to have this sort of abstraction layer because it makes it easier for you to add on a later stage a new graphics API you may want to support. So first, we need to get the data to the GPU. This is a simple copy operation. It gets something to do using PCIe Express. So all the data, like the buffers, vertex buffers, index buffers, all the textures. And this is usually done kind of asynchronous. So when you load a level, usually you have a loading time. And this is usually used to get all this data to the GPU, also to compile some shaders, for example. And then when you're in the level, you kind of still need to like stream ahead like all the data what will be needed in the future, so that not when you need a texture to access, that it's already on the GPU memory and not still somewhere on system memory, because then it takes a lot of time and you will see the spikes in your frame time. And then we also have the list of commands we recorded. So usually you record them for every frame because they vary depending on the frame. For example, if there's an explosion, we need a different set of commands if there are no explosions. And these very common commands are listed here. Just a quick overview what they mean, and you will understand later why I exactly listed these ones. So the first one is bind pipeline. And just that up, this VK stands for Vulkan. So these are Vulkan graphics API commands, but the equivalent exists, for example, on DirectX 12. So the bind pipeline is just a command that sets the GPU into the right state. So all the different settings the pipeline can have are defined here. And what the pipeline exactly is, I will talk about in detail in the next section of the talk. Then bind vertex buffers is just to tell the GPU which vertex buffer it needs to access for the following commands, the same for the index buffer. And then the draw command is basically the command that tells the GPU, okay, now using all the previous settings from the pipeline, the vertex buffer, the index buffer, now it actually should process the data according to all these settings we determined before. Okay, now we have all the data we need transferred from the CPU to the GPU and also all the commands. So now we can actually leave the CPU and go to the GPU. And when talking about graphics programming, we also have to talk about the graphics pipeline because it's the main logical context how the GPU operates on your data. So it defines how the data it looks like, so the input data, in which form it has to be, so that the GPU can understand it and work on it. Then the different stages your data go through, and then also how the output will look like. And then also in this pipeline, there are different stages. And there are certain stages, usually called fixed function stages, that you can't modify. So they are there for a specific purpose. And you will see later, they're also referred to specific hardware units on the GPU. And they are designed specifically to do this single task. This is different than to the shader stages, because the shader stages, they compute code you as a programmer write. So here you can tell the GPU exactly what it needs to do. Then we have the graphics pipeline, and next to graphics pipeline, we also have the compute pipeline. And the compute pipeline only consists of a single stage. It's a shader stage, so it's very generic. it can be used not only for graphic stuff, but for any type of problem, basically, which is highly parallelizable. So it makes sense to use the GPU for this kind of task. There are also other pipelines, very new ones. I won't discuss them here because they are so new that only newer generation hardware supports them. There's not much research out there yet. This would be the ray tracing pipeline and the mesh shader pipeline. I just mentioned them here so that you're aware of them. But especially for an introductory talk, they are not as important yet. It's still very important for FECAS to know the graphics pipeline and also the compute pipeline by heart. But the newer ones, they're really still in their baby shoes. So these are the logic pipelines I will cover in this talk. So it's the graphics pipeline commonly used to process 3D models and then to get respective pixels as output so that you see the models on your monitor, and then also the compute pipeline, which can be used for various things, and for example, for post-processing steps. And then when we go on the hardware side, so the hardware also has a pipeline. And later I will map the logical pipelines with the pipeline you actually have in the hardware. And here you already see that I marked 3 different pipelines. One is the Vertex pipeline, then the Pixel pipeline, and the last one is the Complete pipeline. And the Vertex and Pixel pipeline, they together correspond to the graphics pipeline, and the Complete pipeline is the separate thing, and it corresponds to the compute pipeline on the logical side as well. And you see here already that even though we have 3 different pipelines, they access the same hardware units. So this also means they access the same resources on the GPU. And Vertex pipeline, it's called Vertex pipeline because the data the GPU operates on is, so the smallest work item is the vertex. And at some point during the pipeline, basically these vertices get transformed into pixels. And then the GPU works on pixels. So then the smallest work item is not the vertex anymore, but the pixel. And for compute pipeline, this single work item is called a thread, and what it operates on is totally up to the program. So I will quickly go through all the hardware stages just to give you an overview so that you're not completely confused, and later I will go in depth and compare the hardware stages with the logical pipeline stages as well. So in the beginning, we always have the command processor. The command processor is the interface between the CPU and the GPU. So when we send all the commands from the CPU to the GPU, they always first arrive at the command processor. You can kind of also think of it as being the gate to the GPU, and the command processor will process the commands and then also basically tell the GPU what to do with them. The geometry engine is responsible for all the geometry type of data and process that needs to be done. So it knows about the topology, for example. So if you have vertex buffers, it knows if you're operating on points, lines, or triangles, for example. So if 3 vertices span a triangle, or if just 2 vertices span a line. So for example, if you render a wireframe, you're working on lines and not on triangles. It also has the information about the connectivity information, so which 3 triangles span which 3 vertices span a triangle, and all this geometry associated information will be stored in the geometry engine and also processed. The shader processor input accumulates work items. So in the Vertex pipeline, it would be that it accumulates vertices. The vertices will be received from the geometry engine, and then as soon as there are enough work items, it will kick off the work on the dual compute unit. Enough work items means specifically on the RDNA architecture that we either have 32 work items or 64. It depends which shader type is running and on other like more driver-specific stuff, but in general, either 32 or 64 work items are needed, and then we can actually start work on the dual compute unit. The dual compute unit executes the shader program. So this is the part in the hardware that will execute the code you as a programmer write. And the dual compute units, they can read data. So for example, they can read the vertices you submitted, textures, different kinds of buffers, constant, and it can also write to memory. So it can write to textures, it can write to buffers if you want to. And then additionally to this writing to memory, it also exports specific kind of data. So when we go through the Vertex pipeline, it will export the position after the transformation, for example. And for this export, the shader export is responsible. And as it says, it's handles specific output from the dual compute unit, which is dependent if you're now on the Vertex pipeline or on the pixel pipeline stage. And then also dependent on which pipeline we are, it will proceed either to the primitive assembler or to the caller and def backend. Now, since we are still on the Vertex pipeline, we will go to the primitive assembler. And the primitive assembler reconnects all the vertices so that we have a triangle again. And then the triangles get converted to the scan converter, and the scan converter does the actual rasterization. So the scan converter basically determines which pixels are covered by this triangle. And this is also the stage where we go from the Vertex pipeline to the pixel pipeline, because all the stages after the scan converter will operate on single pixels. So scan converter determines all the pixels that are covered by the triangle, and then the pixels get forwarded back basically to the shader processor input. Shader processor input waits again until there are enough block items, in this case now until there are enough pixels, and then it kicks off the work at the dual compute unit. Dual compute unit will process now your pixel shaders. The shader export handles now the output from the pixel shaders, which are the color information for your specific pixels, and then it goes to the caller and def backend. And this wise final output that ultimately you want to display on your monitor. So now let's look at the mapping between the hardware pipeline and the logical pipeline. And to make the mapping easier, I unrolled the hardware pipeline. So now you see on the top row, we'll see, for example, the shader processor input twice, also the dual compute units twice, the shader export twice. But just to make sure these are exactly the same hardware resources, I just unrolled them to make the mapping easier. And so the command processor we skip for now because this is just processing the commands. And then the first stage on the logical pipeline, the input assembler, can be directly mapped to the geometry engine on the hardware side, because this is the stage where the input gets processed, gets assembled, where it gets prepared for all the following work. Important here is to note that the geometry engine already does the first optimization step. Because if we have our vertices, as I said in the beginning, there are vertices that are shared by several triangles. And the naive way would be to just forward all the vertices to the shader processor input, and then we do all the transformations needed on the vertices, even though if the vertex was already processed before, we have duplicates. This makes it in some sense easier because then we don't lose the connectivity information. We can just say, okay, every three vertices belong together and span a triangle. But it comes with the side effect that we do unnecessary computations because we actually already shaded this vertex and we don't need to do it again. So the geometry engine basically has a cache for vertices that were already processed. And so it basically tells, okay, this vertex is already shaded, we don't need to do it again. And it also stores the connectivity information that would be lost by this process, because now we can't say anymore, okay, every three vertices span a triangle, because some vertices we don't even process anymore because there would be duplicates. And of course, if the cache is full, and then some old vertices fall out of it, and if they appear again, then we need to reshade them. This means as a program or when you like generate your vertex buffers, it makes sense that triangles which share a vertex, they are also kind of close in the vertex buffer so that you make better use of this cache. Then the shader processor input is somewhere in between the input assembler and the vertex shader because it retrieves all the vertices from the geometry engine and then starts the work on the dual compute unit. So what the shader processor input does, it waits for all the vertices to arrive. Then it chooses an available dual compute unit. It also configures the dual compute unit. So it reserves the resources. So all the registers needed. It also sets the program counter on top of your vertex shader program. And it also initializes the registers for your shader. And then ultimately, after everything is set up, it kicks off the work for the dual compute unit. And the dual compute unit, usually what it does on the vertex shader stage is that it transforms the vertices from object space to clip space. It can also attach additional vertex attributes. It depends on your problem case. And the thing here is that usually it does the same transformation on every vertex in the mesh. And this is very parallelizable. And this is the reason why GPUs were invented in the first place, because the problem we are working on here is very parallel. We have a lot of data. So we have like millions of vertices that have to go through all the same computations. And this is also why the GPU is exactly built this way, why the dual compute units look like how they look now. And so on GPUs, you don't have a single dual compute unit, we have a lot of them. The amount depends on cards. So for the RX 5700 XT, we have, for example, 20 dual compute units. Maybe if you read some other sources, we will see it has 40 compute units. It's the equivalent to 20 dual compute units. Or if you look at the new cards, so on Wednesday, we released our 6800 and 6800 XT. And for example, the 6800 XT has 72 compute units. And it's not directly mappable, but in general, you can say the more compute units you have, the more powerful is your card, because you just have more compute units where your shaders can run and you can like kick off more work in parallel. So you have a bunch of these compute units, and each dual compute unit has 4 32-byte SIMDs. So SIMD stands for single instruction, multiple data. So as I said, you have the same instruction for multiple data. So in this specific case, it would be we have multiple vertices that go through the same instructions. So in SIMD, we have 32 threads. And that's why I also said usually the SPI, so this shader processor input, waits for 32 vertices to arrive. In some cases, it can also run in 64 mode. So basically just kick off the work twice on the same SIMD. But the default, so natively, it's 32 threads. And so the package you're working on is always 32 vertices, and then it can get kicked off. Then the two register types we have on the dual compute are vector registers. So they're also 32 bytes. It has one value per thread, and then a scalar register that holds one value per wave. A wave is 32. This is also an optimization, because if we know it is a constant and has the same value for every thread, for vertex shader for every vertex, we don't need to copy it 32 times. We can just have a single copy of it and then just let every thread access this single copy. Then also, due to how the compute unit is designed, and since it's like SIMD, single instruction, multiple data, we also really should make sure that we really have a single instruction, the same instruction for every thread. And this gets complicated if we have if branches in there, because if branches usually mean, okay, just part of the threads maybe fall into the if branch and the other part fall into the else branch. So in this example, for example, if we have the vertex which is based on the tail part of the fox, then we do some foxtail specific things. And if it's part of the rest, so of the body part, then we do other things. This is not an issue if all the vertices are, for example, from the body part of the fox, because then this part is just skipped by all threads. So we can save this and then just directly go to the body part. But as soon as there is one single vertex that falls into the tail part, we also need to compute that. And typically you have a mix, but if it's just one vertex, it's really kind of like not so optimal because it still takes the same amount of time as if you would have a 50-50 distribution. So in this specific example, one solution would be to just split the object into two separate objects so that you have a foxtail object and a separate fox body object, for example. So then, in this case, you would never fall into this problem because we would have two separate shaders without the if branch, and all the code would be coherent. Then the next logical pipeline stages, they are optional and also not too common, I would say. So these are the tessellation stage and the geometry shader stage. I won't go into detail about these stages, but in general, they're used. They can be used to further transform the geometry. A lot of stuff that can be done using the tessellation stage and the geometry shader stage. They can also be done in the vertex shader stage. There are some cases where it makes sense to use these stages, but yeah, these are very specific problems. What I do want to highlight here is, though, that even these two stages, they use the same hardware stages. So all the shader stages, here the hull shader and the domain shader stage, which belong to the tessellation stage, and the geometry shader stage, they are executed on the dual compute units. And since these both stages are for geometry transformations, this means that it also goes routed to the geometry engine. So the tessellator stage is executed on the geometry engine. So just to be aware, even those stages, they access the same hardware resources as the other stages. It's just the rasterizer. On the hardware pipeline, there are several different stages actually associated with this one logical pipeline stage. And the first one is the shader export. Kind of the shader export is also in between the vertex shader and the rasterizer because it gets to transform vertices from the compute units, and then it basically decides if we are now need to do the rasterization or if we are already on pixels, so we need to go to the output merger. And on the hardware side, this would be the color and depth backend. Then the primitive assembler. So the primitive assembler retrieves all the vertices. It also retrieves the connectivity information from the geometry engine, and it reassembles the triangles. And then it also does some post-processing steps. This is also already optimization, what the hardware does for you. So it does custom culling, for example, does backface culling, so that we already discard triangles that are not seen on your screen that we don't need to further process. So it's already doing this kind of things, just to reduce the amount of work that's needed. And then after all these post-processing stuff, the triangles get forwarded to the scan converter. And the scan converter does the actual rasterization. As the name already suggests, it does some sort of scan conversion, but only on a coarse level. So if we have our triangle, and then if we have all our pixels, usually it works on a group of pixels. So it looks on 4x4 pixels, and then it looks if these 4x4 pixels are overlapping the triangle. Actually, not the triangle itself, but the bounding box of the triangle. And this is done by a scan conversion. And then for every 4x4 pixels that actually overlap with the bounding box of this triangle, we go one level lower and test against the actual triangle edges. And then every pixel gets marked as even if it is overlapped by the triangle or not. And then again, we group pixels now in quads, so 2x2. And as long as one pixel is overlapped by the triangle, we send the whole quad to the shader processor input. Why the whole quad? First of all, it's also kind of optimization because since it's a parallel hardware, we try to avoid just working on single work items. And then also pixel shaders, due to how it works, it also needs the derivatives. And these are usually computed within quads. So even if just one pixel is overlapped within the quad of the triangle, we still need the information of the other quads to get the derivatives information, which is needed, for example, for specific operations that the pixel shader needs to do. So, for example, to choose the correct mid levels, if you have like textures and if you're like further away, and so like so that it can. And this is also kind of an optimization already. And so that's why we always have to work on quads. So the shader processor input receives the quads from the scan converter, and then it chooses a dual compute unit, sets it up again. It's the same process as for the Vertex shaders, and then it kicks off the work. And as I just said, since we are sending quads over, it's important that you don't have too many small triangles. Because if you have really small triangles that are only covering single pixels, then you will end up with quads where 3 of the pixels are actually masked out. So even though we need these quads for the derivative information, still the threads actually associated to the pixels and that are not overlapped by triangles, they will be deactivated. And this is, you're basically just wasting GPU resources. So what you want is basically large enough triangles to make the best use of the GPU as possible. And if you have a lot of small triangles, then you will end up just using 1/4 of the capacity the GPU can operate on. And then after the compute unit is done with executing the pixel shader, the shader export forwards the pixels, or also called fragments. This is just DirectX speak versus OpenGL Vulkan speak. Then it forwards the pixel fragments to the color and depth backend. And the color and depth backend, it does color blending in case we have transparent. Also does some other stuff, just like MSA, resolve, compression. It's not really important now what all this means. And ultimately it writes out the pixel color to the bound render targets. And then if you did all this processing at the end, you want to usually display this render target on the screen. So in our example, we are not quite there yet because now we processed our object. So this example was just a fox, but now we also want to add some fancier lighting. And this would be a typical post-processing step. And this post-processing step is also, like this particular example would be a full screen pass. So what it means is that the output render target has the size of your screen. So in our example, we use the just generated render target as input for the next pass. We do some calculations on it, and we output another render target of the same size, which is actually the size of the screen. So we know in advance that every pixel of the output render target needs to be modified. This is just by design of our problem we want to solve. So we know the pixels and which pixels should be covered by the triangle, because we just need to process all pixels of our render target. So how you can do this using the graphics pipeline is that you define a large enough triangle that just spans over the whole output render target. And then the rasterizer will do its job over this triangle and just forwards every pixel to the pixel shader. If your triangle is too small, then you will see that the output will be just for this part of the render type, which is actually covered by your triangle. And this is not what you want, because you want every pixel in your render target to be modified. Another way to solve this problem is therefore not using the graphics pipeline, but the compute pipeline. Because in the compute pipeline, you can explicitly define how many threads you want to evoke. And here you can basically translate threads in pixels, because each thread will basically compute one pixel output color. So as input, you have, again, your render target. You can define this in your compute shader stage. As output now, you have a writable texture of the same size as it would have the render target from your graphics pipeline. And then you just evoke enough threads. This would be the resolution of your output target. And then for each thread, the compute shader just does its job. So it operates on the render target and outputs the color. So this is one way how you could do it. What are the nice things if you use compute shaders instead of the graphics pipeline is that you only access the hardware units that you actually need. So you only access the shader processor input, which is basically accumulating all the several threads and then kicking off the work for the dual compute units. But you are not using the geometry engine, you are not using the rasterizer, so you're not using the primitive assembler and scan converter. So these hardware resources, they are not used by the compute pipeline, and therefore could be used by other tasks you might have at the same time on the GPU. So I talked a lot about parallelization, that you have like several threads running at the same time, working on the same instructions. But since we have several compute units as well, we can run different shaders at the same time that could overlap the work. And you also can have compute shaders running at the same time as Vertex and pixel shaders. And while the rasterizer, for example, is outputting the pixels from your Vertex shaders, so from the triangles, while the GPU is busy with that, at the same time, it can compute shaders on your compute units. So this is just a way how to make the best use of the different stages of your GPU. And then at the end, when we have our final image, we send it over to the screen, usually the sun, either using DisplayPort or HDMI, and then we display it. And that's basically already the end of the talk. Now we have a lot of time for Q&A. And just at a short note, I want to thank Dominik Baumeister and his talk, because my talk was actually highly inspired by his talk. So yeah, and now let's see how Q&A works. And I think, yeah. So I see one question, and I think I just read it out and then answer it. What would you say is the most common mistake in trying to optimize GPU load, where because of how the hardware works, there isn't really a significant gain? So when you try to optimize GPU load, it's really important to first identify where the bottleneck is of your GPU load. So for example, if you are bound, for example, by the rasterizer, because the rasterizer is processing your primitives and then it's outputting the pixel shaders. But if so many primitives are coming in and there's like a fixed rate in how fast it can produce more pixels, and if you're bound by that, it doesn't really make sense to speed up, for example, your pixel shader, because even though if you speed up your pixel shader, it will still be bound by the rasterizer to produce new pixels to generate. So I think this is one of the most important things that you need to do. First, identify the bottleneck, and then try to speed up where actually the GPU is limited. Otherwise, you won't see any gain, obviously. Is pixel shader the same thing as fragment shader? Yes, it's the same thing. So pixel shaders usually used when you are using DirectX 11, DirectX 12, and when you are on OpenGL and Vulkan, you usually deal with fragment shaders, but they're exactly the same. Okay, still a lot of time for more questions. Also, if you want me to re-explain some slides, just add it in the Q&A Slido thing, and I can go through it again. Also, since I'm waiting for new questions to arrive, if you want to learn more about graphics programming in general, or also how our hardware works, you can go to gpuopen.com. There you will find a lot of tutorials. You will also find a lot of different talks. For example, the talk I mentioned here from Dominik Baumeister, you will also find the slides there. So if you want to find more resources about this specific topic, you can check out this website. Okay, new question, right? RDNA architecture greater than ARM. I don't really understand this question and what do you mean? So the RDNA architecture is AMD's new architecture, which all new GPUs are based on. So the first GPU based on the RDNA architecture got released last year in June 2019. I think it was June or July, but in summer 2019. And just now we released our next generation GPUs based on RDNA 2. So there's slight modifications in the architecture, but the overall concept is still the same. Our computer is the best tool to do post-processing. I'm always careful to say the best because it depends on a lot of different things. But I would say in general, I usually recommend to use compute shaders for post-processing. Because, for example, also if you have your complete post-processing on compute shaders, you could place them on the async queue, which I haven't talked about in this talk. But if you have them on the async queue, you could potentially overlap it with the beginning of the next frame, which is typically very geometry processing heavy. So usually in the beginning of the frames, you do G-buffer passes, you could also do shadow mapping. And this could be overlap. So you could overlap the end of the frame with the beginning of the next frame. And this requires that your whole post-processing is on compute shaders. How does the pipeline change when taking into care ray tracing? So ray tracing just has a complete different pipeline because suddenly we are not using the rasterizer anymore. So we don't have triangles where we need to figure out which triangles covers which pixels, but we are basically at the scene representation using some sort of acceleration structures, and then we have rays. So the single work item would be a ray. So you usually have a shader that generates the rays, and then the shader which does the intersection part, so to determine which objects your ray intersects, and then also to define the shading of this intersection point. So all this stuff I talked about, you have the vertices, and then they get transformed, you have the triangles, you have to figure out which pixels are covered there. They're just not relevant anymore if you're looking at ray tracing, how it works. From what I understood, it's better to avoid if statements altogether. Is it right? Yeah, in general, yes, because if statements, they can lead that threads taking different paths. So what you want is really coherent code. You want that every thread goes through the same path. And if you have a lot of if statements, then the probability that every thread takes the same path is obviously less. So if you can avoid them, then yes, that's in general good advice. Okay, any more questions? Another thing I can mention here is that it also makes sense that you have, so for example, if you have a problem to compute, for example, compute shader, if you can distribute the work on a lot of threads. So if you have, for example, a potential that a thread does a lot of steps, or you divide the steps to multiple threads who can work on this at the same time, then it's usually advisable to do so. Because if you have more threads that you can have run in parallel, then you have the GPU also occupied more. So you have more threads running on the GPU at the same time. And then in some cases, the threads have to wait, for example, for data to arrive. So if you're reading from a texture, this is very time consuming. So if your computations that are really fast, and then you have to access some data, and it has to go through the GPU memory, and this takes really a lot of time. So while these threads are waiting for the data to arrive, usually they are kind of paused, and then the GPU will go to the next batch of threads and start working with them while the other threads are still waiting. So that's why you really want to have a lot of work on the GPU. And that's also why already on the CPU side, you should record the commands in a way that you have enough work for the GPU to be busy. So if you just have work for one thread, or okay, that's kind of extreme, but just 10 threads, and then if the threads have to wait for the data, basically the whole GPU waits for these threads and that the data is there, and you don't have other work at the same time that could be executed. Okay, next question. What is the most common GPU optimization that you do? Is it more like fine-tuning the rendering on the CPU in the engine, or more like fine-tuning shaders? So usually on what GPU bound. So that means also that I don't really do optimizations, fine-tuning on the CPU, but of course, if they're CPU bound, you have to look at that. So it also depends on your game, if it's CPU bound or GPU bound, because it doesn't really make sense to do fine shader tuning if the bottleneck is on the CPU side. And bottleneck on the CPU side could be that it takes too much time to generate the new commands. So the GPU basically processes all the commands and then waits for the CPU to get the new commands. Or also if you have a lot of synchronization between the CPU and the GPU going on, that basically stores the GPU and just lets the GPU wait for the CPU to give a certain signal. So first you have to, if you want to do any GPU optimization, you have to be sure that you are also GPU bound, because otherwise you won't see any gain. And then if you are GPU bound, very common optimization is, even especially nowadays with the explicit APIs, is that you look at the barriers, so how the GPU synchronization works, so that you don't artificially have very sequential work, but that you really allow your different workloads to overlap. And fine-tuning shaders is actually quite late, usually in the optimization stuff, because most of the time it's more okay, barriers are placed very incorrectly, or that the formats don't really fit, or your G buffers are really fat, so they need a lot of memory, stuff like that. Or in general, the memory management is also very critical, because allocating and deallocating resources takes a lot of time. And then, of course, when you go into shader tuning, usually you look at the longest shaders and try where we can speed up there. And common optimization strategies are there, for example, scalarization. This means to get rid of this, for example, if statements that to make sure that all the threads really take the same path. So this means if there is that the result will be the same for each thread. So this is called scalarization. So for example, that you only take into account the result of the first thread in your whole rate and stuff like that. And then also when you are on compute shaders, You can make use of local data share. So this is basically special memory the compute shaders explicitly can access. And this is a way to share data between threads within a single wave. So there are a lot of different things you can do when you go into fine shader tuning. Why is it that Vulkan isn't used as much as pipeline in games at the moment? I think you mean, why is it that Vulkan isn't used as much as DirectX 12 in games at the moment? Because otherwise it doesn't really make sense. And I can only guess, but as far as I know, if you, for example, want to, because Vulkan, so usually the choice of graphics API is based on a lot of things. And one major factor is the platforms the game need to be run on. So for PC, you can use Vulkan, DirectX 12, DirectX 11. But for example, for the consoles, you're kind of restricted. Also, if you want to use some cloud gaming platforms, and there is actually kind of determined by the platform which API you have to use. And this usually is a high factor in the game, which API they choose. What do you consider a GPU-bound workload? GPU-bound workload, the final frame time is determined by either the GPU or the CPU. So if it's GPU-bound, then basically your GPU is all the time busy. So if you have a frame that takes, for example, 50 milliseconds, and during these 50 milliseconds, the GPU is always doing work. And then as soon as the frame is finished, it just restarts doing work. But while it's CPU bound, the whole frame time is still 50 milliseconds, but now during this 50 milliseconds, the GPU is actually not always doing work. You will see some gaps when the GPU is not doing anything, especially just waiting for new work to arrive from the CPU. So speeding up the work the GPU is already doing doesn't help in this case. It will just increase the gaps where the GPU is not doing anything and is waiting for the CPU to produce new commands, new data that the GPU needs to process. And to determine if it's CPU or GPU bound, you can use different tools. One would be Radeon GPU profiler, or GPU view, where you can basically see, okay, where do we have the gaps? So Radeon GPU profiler is an AMD specific tool. GPU view is any kind of GPU, and there you should basically see, okay, this is the workload the CPU provides, and this is the time when it gets sent to the GPU, and then you can see where you see the gaps basically. And if it's CPU bound, then you will see gaps on the GPU workload side, and if it's GPU bound, then you will see basically the gaps on the CPU side, or basically you won't see any gaps on the GPU side. Is optimizing GPU for the console is different from optimizing for the PC? Yes, because on the console, you know exactly what's in there. So you know exactly the GPU, you know it, like all the hardware details, it's known, and you also know it won't change. On PC, there are a lot of different system configurations. A lot of different, not only the GPU can be different, but also the CPU is different, the amount of memory available. And then also the drivers are different, because the drivers also have to take into account that how the GPU interacts with the CPU is also a bit different. They're usually not that close, and it's like two separate units. And then of course also on PC, you also put one into APU. So if the graphics card is actually integrated. So on PC, you have a lot of different configurations, and you need to program in a way that it's not only good for one configuration, but good for all configuration, basically. And then, of course, also on consoles, you have, as I said, just one GPU, but on PC, you not only have like different GPUs from one vendor, but also different vendors. And each vendor has their own driver, which can act differently, and then the GPUs have different architectures. And so it is quite different. Do you think NVIDIA and ARM could create a new super RISC processor to be world beating? Maybe. No idea, to be honest. Okay, I think we are actually done with the time. So thank you a lot for joining today and hope you had fun, just as me.